So, just wondering, okay, so homework 7 and homework 8 are due this Friday. Are they going okay? So this is my personal graph that I got for the fill prime Q implementation. Does this look similar to what other people got? Yeah, about similar, okay. Yeah, cool. Is this similar to what people are getting for sorting? Yeah, all right. Well, it's kind of interesting, right? Because, yeah, like, you know, usually when you think, like, oh, when you multi-thread something, it means that, well, the more threads you add, the faster it'll get. But here we can see that there's very clearly kind of like a low point right here. This is, right here is kind of showing, like, where the smallest, or like, yeah, where it takes the least amount of time to complete. Notice that when we go from, I don't know, this looks like about maybe 4 threads up to like 8 threads, there's not much of a change. Like there might be a little bit of a dip down. But now the question to you is though, okay, if we move from 4 threads to 8 threads, so notice, yeah, the time that it takes to finish stays the same, but will our CPU utilization also stay the same, or will our CPU utilization go up? Yeah, so it's gonna, our CPU utilization is gonna go up. So our like computer, even though maybe we're gonna run to make, is that everything is a trade-off, especially when dealing with, yeah, with multi-threading. So if you were asked a question that was like, oh, like on this graph, where is, like at how many threads is the performance the best? So I guess what you would probably do is you'd look at the .txt file that was also generated. So in this case, so for how many threads will it execute the fastest? If you just look at this. Yeah, wait, tell the person next to you. I'm hearing people whisper it. Yeah, okay, it looks like it's about 6 threads happens the fastest. Yeah, but if we go up to like 8 threads, you can see it only like marginally gets like slower. Also, if we go down to 4 threads, you can see it only marginally gets slower. So if maybe you wanted a nice trade-off between like, yeah, power utilization on your computer, like good battery life, but also speed, then what would maybe be a different like good number of threads to have on this application? Okay, tell your person next to you, what is maybe a better number of threads to be running with? Okay, yeah, so if you were an engineer, and you know, if your boss came to you and was like, oh, make sure that people's battery lives aren't completely destroyed, but please make it faster, and you multi-thread it, and you have to set a hard-coded number of like threads or something, how many, like personally, how many threads would you pick? Okay, yeah. You pick 6 still? Yeah, that's true. But it is only like marginally better than like 5 threads or than 4 threads. But using 6 threads may use like 30% more power than just using 4 threads. So would anyone here use maybe 4 threads instead? Yeah, so that's so I agree. So someone asked a good Piazza post a while back about one of the questions in the docs. Let's see. It was kind of weirdly worded, so I just want to, be a little bit more specific here. Let's see. So yeah, it says for what number of threads is the performance the best? Come on, there we go. Yeah, for what number of threads was the performance the best, but what would be the actual best number of threads to run this job on? So my interpretation of my own words that I put here, I would imagine that you say for the performance being the best, that's how, like that is for how many threads it takes the least amount of time to finish. But then what would the best number of threads to run this job on, I would consider this to be like if you want to now also, like maybe you also care about power efficiency. Okay, yeah, makes sense? Good, okay. Is this gonna change anyone's answers on your homework? Okay, yeah, so go and change that. Tell the person, or tell tell your friends who maybe aren't here today, make sure that they also go and change this. Okay. So today, like I said last week, so I've kind of ran out of official material that I wanted to talk about, but today I have a brief lecture prepared on parsing, because I think a lot of you probably at some point need to write your own compiler, parser. I've personally, for the emulator project, right, I needed to have a way to convert from assembly into the .slug file. So I personally, that's a real world example of where I wrote my own assembler, compiler, parser thing. So that I'm certain that in your careers you will need to at some point write some sort of parser. So I'm not the most qualified person to talk about parsing, but I figured it'd be fun to just kind of dump everything that I kind of know about parsing. So that is my plan for today, and then we will finish with a quiz, which will also be a good preparation for getting you thinking about your final exam, which will be next Thursday, which we will also briefly mention today. But first I want to start with parsing. Okay. Yes, so this file right here, does this look familiar to anyone? Okay, yes, no, never seen this, yes, you've seen this. Okay, yeah, this was the example that we ended with last class. And the idea with this is that you pass in some string and you parse it as an integer. So here you put the radix, or I guess the format. You say if it's a binary value, or if it's unsigned decimal, signed decimal. And inside all of this, we converted all of these checks here. We converted these to non-mutable expressions, non-mutable variables. We marked them all as const. This made our code kind of more readable, at least in my opinion, and in a lot of people's opinion, because it's really nice because you can just immediately look and see. It's CH is signed decimal. It's okay, this is very clear what this flag is doing, and it's never going to change because it's marked as const. And I can see okay, so CH, this is just this is the current character that we're dealing with. So it's very clear, and we actually don't need any comments in this entire function, because this function itself actually is self-documenting. Because when we look, it's what is this variable for? It's not like we labeled it as x or something. Instead, we labeled it exactly what it is. We're saying does this work as a binary value? Because if we get the number 9 or something, then it wouldn't be a binary value. So okay, so this was our function that we made look pretty. If you remember, so this was one of the final exam questions from the last course offering. The question was just take ugly code and then make it pretty. And this was the solution for the pretty code, which is kind of just making it more self-documented using non-mutable expressions here. But the now question is, well, okay, so cool. So now we have parse int, but what if we wanted to maybe parse something a little bit more complicated? So maybe we want to parse some sort of code file. So what I want to show you is this other implementation that I have here. So this is a completely different example, and let's quickly look at my main function. So here I have this main. It says please enter a prefix expression. Okay, has anyone heard of prefix expressions before? Okay, cool. So I will briefly give a demonstration on that. So this often comes from, historically came from calculators, and the historical way that calculators would read in button presses, because you just had to be very careful with the way that you could implement your calculators to make sure that the logic involved wouldn't be too expensive or too complicated. So one of the methods for actually punching in expressions on a calculator was something using prefix expressions. So for example, if we want to add the numbers 1 and 2 in this calculator, then we would type in first plus, and then we would say 1, and then we would say 2. So if we typed this into the calculator, then maybe hit enter, then this would return the value 3. Okay, and this is because first we give it the operation, then we give it the first expression, then we give it the second expression, then once we're done, then we perform like all of the computation, and we return the final value. Okay, cool. So just showing you this is something that calculators used to do. Now, of course, we probably would just do like 1 plus 2 or something. But this is a little bit easier than doing, it's called infix. Infix would be if you're doing like 1 plus 2, but doing prefix is a little bit easier. Okay, but if we wanted to do a slightly more complicated expression now, if we wanted to like multiply the numbers like 4, 5, and 6, then first we would do multiplication, and we would do 4. Well, if we did 5, well, this would now end our expression. So we wouldn't be able to enter anymore. Like this would just evaluate right away. So instead, what we can do is instead of saying 5 right here, we can actually just enter a whole nother expression. So we could say times, and then 5, and then we can say 6. So now, what will happen is, so we feed all this in, and then it will notice like, okay, so this group of 3 right here, this is like a full expression that we can evaluate. So this right here will get evaluated to what value? 30. Okay, so this will become 30. And then, okay, well now can we solve this? What is this? Yeah, 120. Cool. So therefore, yeah, that is kind of the algorithm to take a prefix expression like this and then convert it down into something more simple. Cool. Okay. So let me show you my this main file just working, so we can just know like sanity check. It's all good. So cd parse. Actually, I'll keep that open. Okay. I won't show you my parser just yet, but think about what the parser should probably look like. So, okay, I'll do just make and /main. So here it says, yeah, enter a prefix expression. So now notice that we have this parse function, which I implemented, and it takes in std in, and now we can enter an expression. So we could say, yeah, we could do the same one. We could say 4 times 5, times 4 times 5, 6. Right, cool, good. Okay, so this should work. There we go. So, and it actually even prints out what the expression is in infix notation as well. And then, yeah, then it goes and prints out the result. So, cool, okay. If you were to implement this parse function, then how would you do it? So this is the question that we're going to be spending like 25 minutes on, is how do you implement this parse function in the best way possible? Okay, go and chat with the person next to you for like 30 seconds and be like, oh yeah, like the way I would do it is have like a bunch of if statements, and the first if statement would have this and that and that, or something. Okay, go and explain to the person next to you, how would you do this? Okay, cool. So any thoughts? Okay, yeah, up there. Okay, sure. Regex and recursion. So maybe we could just search for like the first integer or something, and then after that, search for the next integer, or like we could search for operations first. Sure. Okay. Any other thoughts? Let's just get a couple ideas. Yeah. Any other thoughts? Yeah. Sure. Okay. Stack. Yeah. I could see that. So maybe you add, I guess, the operation to the stack, right? Okay. I could imagine something like that, sure. Okay, well, so if we, do regexes, or if we're, like, grabbing things off the stack, well, how do we, what are the actual things that we're maybe putting onto the stack, or putting in this, like, data structure? What are we putting in? Because also notice that we, at least in this case, we have this, like, root pointer, and then we call print on this root pointer. So that gives us a little bit of a hint. So like, what does this data structure, what does root like hold? Yeah. Sure. It's the expression to evaluate later. Yeah, but what do we store? Like, what is the expression stored as? Yeah. Yeah. So I agree with that. Yeah. So it'll be a tree. And let me show you. So this is actually called an abstract syntax tree. So we're not going to be using a stack. This is abstract syntax trees are kind of the most typical way of implementing parsers. So what we have in this case, so we have this abstract syntax tree node, and notice that this has no members, but it has these two pure virtual functions right here, which are solve and print. And then we have three nodes past that. We have AST_int, AST_var, var because I didn't show you this, but the implementation also supports like variables, like we can put in like x or something. And then we also have AST_op. Okay, well, let's look really quick at AST_op. So what members, what like variable members does AST_op have here? We can see it has this car op. What is this? What are possible values for car op? Yeah, right. Yeah, exactly. So this will be like plus, minus, divide, multiply, right? This is just the operation. Then we have left and right. Okay, so what are these? Yeah, perfect. So it'll just be the integers on left and right. But also, it may not be the integers. Remember, it may also be just the expressions on the left and the right of the operator. Because you could have an operator require like a bunch of, you could have the operator work on longer expressions. That was like the whole example where, we can have multiple operations. Cool, okay. So then if we look at then AST_var, so AST_var, what is the only member that this has? It's just a string, right? Because it's just the name of the variable, if it was, int I or something. Then we have the AST_int, and all this has is just value. Okay, so this is the data structure that abstract syntax trees are this is the structure of abstract syntax trees. And any compiler that you ever work on, or that maybe you write from scratch, ideally should kind of fall under this format. And like I will occasionally work on Verilog and system Verilog tools, and so I'm regularly kind of getting my hands dirty with abstract syntax trees. In case, so I have seen these quite a bit. Okay. Cool. So if this is the goal, right? So main, the idea is it calls parse, and parse will generate the big abstract syntax tree, which is just a bunch of nodes. The parent node of all of them will be AST node, but each individual cell, like each individual object will be a different variant on the AST node. It'll either be an operator, it'll be a variable, or it'll be an integer. Okay, cool. So now I've been beating around the bush. Let's actually look at what parse does. And this implementation, it's somewhat straightforward, somewhat easy, but there are a few problems with it. But okay, let's take a look at it. So what happens? So first we grab, so we have this in stream. If you remember, we were grabbing stdcin. And so what we do is we just grab like the first member out, and then we check like, okay, is that member an operator? Like, is it minus, plus, divide, multiply? If so, then go and create this AST operator object and assign the operator to whatever the current token is, and also go and parse out the left and the right that comes afterwards. Okay, and then after that, well, if it is not an operator, then what we do is, well, maybe we can just assume, this is maybe not the best thing, but maybe we can just assume that it's an integer, and if it's an integer, then we create AST int, but if it's not an integer, then string to integer will throw an invalid argument exception, so then we can go and just catch that exception and then assume that it's a variable. Probably not the best strategy. If you remember, what was one of the issues with like try-catch blocks? Maybe why is this the best thing? There's a few reasons, but yeah. It's very slow, right? Yeah, that's one of the biggest problems with try-catch. So actually, this isn't maybe the best thing, but it's at least pretty straightforward. Okay, cool. Making sense? Cool. There's a couple issues with this. See if you can decide what they are. I'm going to type in an example that will not work. See if you can beat me to it. What is an example that will not work? Okay. Yeah? Sure, okay. So if we did times 4 5 times, we should probably expect this to be what? It should probably be an error, right? Instead, what will probably happen is it'll just truncate off this last bit. Yeah, okay. Sure, so that definitely is an issue with it. Another issue with it is, maybe our variables, maybe we expected them to like start with a letter, and then after that, maybe it's allowed to have like a number or something. So, okay, so if we do like times, we can do x and 5. And I think I hard code x to be the value 10. Yeah, so right here, I hard code the value x to be 10. Let me just quickly run this so you can see generates 50. But okay, if I now wanted to do like start, I don't know, x 5 or something. So notice that I have no like white space in between the two. And I run this. Notice that it hangs because like it's expecting it to be over. If I like exit out, officially, if I say like, no, this is the end, then it'll segfault. Okay, that's not good. Yeah, I mean, white space in general is just not great. Like maybe we would want it to be able to support like something like this. I don't know, like that. So we say like 45 times 6 minus 7, but instead this will just say like undefined variable. Okay, well that's clearly not a variable. Yeah. So the issue is like, we could go through and we could go and implement this a little bit better. And we could support like every little edge case, and and that would be totally valid, fun project. But now imagine that you're throwing in like if statements and throwing in like new keywords. And what would happen is this parse function would grow absolutely huge. And yeah, now think of what the parse function is for like C and C++ or Python or JavaScript. Like these parsing out large code blocks is extremely difficult. And so actually, generally, no one will actually write like a parse function like this. Instead, they will use a different tool called Bison and Flex. People heard of this before? Bison and Flex? Okay, cool. So I'm going to give a brief overview of that. Yeah, it's exciting. Okay, so the issue is that like this example, it's very elegant, it's very pretty. The issue with Bison and Flex is we get to a lot of like boilerplate, so kind of stick with me. But okay, so here I have my new main function. Notice I have this other function called yyparse. In this yyparse, this comes from the auto-generated code from Bison and Flex. And notice that it's like the main function is almost entirely the same. The only difference is, yeah, just this name is slightly different. And then, so the first file right here, so this is a flex file. Flex, I'm not sure what F means, but LEX, that is like a lexar. This is for determining the tokens. So what we had last time in order to determine the tokens, if you remember, so let me show you. So the way that we determine the tokens is we have this input stream, which will just be stdin, and we just grab tokens which will be separated out by white space. That's what like this will do. So a token is just surrounded by white space on either side. That is our old implementation. But yeah, maybe we want to be able to support like skipping white space, or maybe we want to be able to support like parentheses or quotes, or I don't know, things just get like extremely complicated extremely quickly the more features that we add. So first we create this flex file that declares all of the different possible tokens. Okay, so here like we're declaring our operators. Here we are declaring an integer, and you can see that we are returning like the integer value. And then also here we are returning the name of the, we're returning the variable name. And here, yeah, we're skipping white space. So here we go. So this generates all of the tokens. And then we can take these tokens. You can see, so there's integer, and then there's variable. And then we can go into our Bison file, and it's called Bison. Actually, I won't get into why it's called Bison. But anyway, so this is our Bison file, which will create the actual parser. But it takes in the tokens, and you can see right here, this is kind of the most important part. Actually, maybe this part. So you can see that it expects there to already be an abstract syntax tree type structure where we have integers and we have variables. But then we also have the different types of operators. So we have like plus, and then we have expressions on either side. And notice, though, that like this whole thing, this is labeled as an expression. So it's cool. So we can say, like, oh, if we ever encounter, this is just like it's going to generate the parser code for us. So it'll say, if we ever are like fed in a long string that, yeah, maybe it starts with a plus sign, then that means that now match it to be like this style, where, yeah, first it starts with a plus sign, then go and expect two more expressions. But an expression is of this form, so it could be either an integer, or it could be a variable, or it could be another one of these operators. And that would be the left expression. And then the right expression would be the same thing. And then what will happen is if the parser ever encounters one of these structures, it will convert it now into this line of code, which will create a new abstract syntax tree node, depending on whatever the passed-in like expression is at any point. Okay, it's kind of a lot, but absorb this for a second. It's very cool. This is the main way that all compilers are written today, is using Bison and Flex, and this is kind of the most important kind of part of all of the code. And yeah, what you'll see in like large coding projects is you'll see like thousands of lines of code that are just describing the different ways that different tokens interact with one another. Yeah, question? Absolutely, yeah. So the syntax is very similar to Haskell, yeah. This is actually, like Bison is considered a functional language. Yeah. Yeah, it's cool. Okay, well let me quickly run this. So let me cd. Okay, so I just removed all the files. So yeah, you can see I still have my ast.h. So this has the different, this has ast int and var and op. And then, yeah, I have my Bison file, which is generating the parser. And then I have flex, which determines how the tokens are generated. And then here is my main. And now I can go and compile this. Make. And I actually need to do make prefix. Okay, and you can see, so first what happened is, yeah, we ran Bison. Bison is an application, and it was run on our bison.y file. Then we ran flex, and flex was run on our flex.l file. And this generated these intermediate files right here. So if we want, we can actually look at the parser that was auto-generated for us so that we don't have to write our own like parser code. So here is the Bison generated file, and it's kind of a behemoth to try to look through. But if we want, we could like search for like minus. Do I have minus? Wait, what's it called? I guess I didn't call it that. Maybe we can just do slash. No. Is it star? No. Oh, here we go. Okay. Good. Yes, cool. So here we go. You can see that this is our like big case statement, depending on like what our current like character is on, and like depending on the current state that the parser is in, and we can see like, oh, if it finds that the in the case where we are currently dealing with an integer, then go and create a new integer, and then it will return this integer inside of our abstract syntax tree. And so in this case, yeah, I mean, there's how many lines of code generated? There's 1,300 lines of code generated. But what's really nice is it makes sure that like every edge case possible is managed. Yeah, because this is the same parser generator that is used by like every compiler. So it's like very well verified. Okay. Any questions on this? It's kind of fun. Yeah. Absolutely, yeah. Ooh, that's something that would be a super cool demonstration, like a cool live demonstration, but I don't know if I would be able to do that right now. Maybe, wait, hold on. Let me see. You know, what you could probably do, all you would have to do in order to do that is you would just change it like that. And then in theory, that should just work. Actually, that might work. Unfortunate. Oh, my bad. This would be now 1. Is that fine? Okay, maybe. Is this going to work? 1 plus 2. Oh, look at that. Cool. Yeah. So, yeah, great example. So, and it's like very, very visible. It's like you can see, it's like, oh, if you ever have this expression format, then this is the same like thing as, yeah, I don't know, it's very visual. Like you can see like when you have expression plus expression, then it will generate the code for you. But you can see like this is valid grammar. That's like the official term for it. It's like when you have a language, you describe the grammar that's associated with it. So this would be the allowed grammar. Yeah, I think it'll fall apart the second that we play around with it more because it needs like parentheses, and that's not something that I would want to do in live demonstration. But yeah, I don't know, pretty sick. All written in C++. Yeah, notice Bison and Flex. Yeah, the most common way of generating parsers all uses C and C++. Okay, feeling okay? Good. There we go. Now you've seen it. And I know what's going to happen is you're going to go home and be like, never going to need that. And then literally like next quarter, it'll be like, oh no, I need my custom parser. Like, oh, I need to write a custom language. You're going to be like frantically going back and finding this lecture and finding this code. And you're like, oh, like thank goodness that I have like somewhere to start off on. Yeah. It's not something, it's something I feel like that everyone needs to like relearn every time that you like write your own kind of compiler from scratch. This syntax is honestly like, most of it's just boilerplate. This is the only interesting part. Okay, so the quiz I want to do in just a couple minutes. It'll be a little bit longer, so we'll start in maybe about 5 minutes. Before that, yes, the final exam. So I talked about it already a little bit on Friday. So the format of the final exam is there's going to be a multiple choice portion that is individual, not with partners, and I will not be kind of going over all the answers like how I usually do for the quiz. You'll just need to sit down and do it. I highly recommend that you make a cheat sheet. It will not be open like computer or anything, so you will just have to go off of stuff from the cheat sheets. What I recommend doing is printing out maybe all of the quizzes. You are allowed 1 page front and back. It is allowed to be printed though, so you can just like get the text really small. But also like maybe double check that you have all your notes compiled. Maybe I'm going to pull something from a lecture where I've provided the code files. Maybe it'll be something from a final project bug that someone was running into that I thought was a really interesting bug. So that will be the multiple choice portion. Yeah, question?
Will the majority of it be similar to the quizzes?
So the questions will be almost identical to quiz questions. Yeah, it'll be like, here's some C code. What is the output? Or it'll be like, oh, if you have a unordered map, then what is the insertion time? Okay. Actually, what is the insertion time of an unordered map? So O of 1. Yeah, O of 1. Okay, cool. What is the insertion time of a vector that has a size less than its capacity? Okay, also O of 1. What is the insertion time of a vector where its size equals the capacity? O of n. Okay, yeah, because it would have to copy everything into a new vector, right? Okay. Okay. I am going to, oh yeah, question? The multiple choice portion will be on paper. Yeah, make sure that you bring a pencil to the exam. Yes, question? On paper. Yeah, we will provide a Scantron for you. Yes. Absolutely, yes, exactly. So, okay. Then we finish the multiple choice portion. I think the multiple choice portion will be about 1 hour. Then the coding portion will begin. You will have about an hour and a half to do that portion. And it will be 3 questions where you are given code, and it is your job to do everything that the question demands of you, and you will also need to submit to Gradescope. There may be an auto grader just to briefly kind of like do a sanity check. You might just check that the files are there, but it may not actually run your code. So it is your job on your computer to verify the code works. So it will be a coding final, and you are allowed 1 partner. And I put out a Google form where you can either choose your partner, or you could also choose not to have a partner if you want. I know it can be kind of stressful to be just given like a random partner. Some people may prefer to work alone, totally fine. I will say that the final is designed to be taken in partners, so it is beneficial if you have a partner. If you do not fill out that form, then you will be assigned a partner at random. Yes, cool. Also, I'm going to give a bunch of information, and then we can have questions. Okay, so you will also need to bring in your laptop. You'll need to make sure that you have compilers installed, like VS Code or whatever IDEs installed. If you've been working off of your desktop computer only and you don't have a laptop, it's your job to quickly go and borrow a laptop from a friend or something, or borrow one from the library. You're welcome to do that, but you must come with everything downloaded and set up. Maybe just verify that everything's compiling on like your final project or something. Yeah, we had a couple people who were like, didn't bring their laptop last course offering. It's like, well, I don't know what to tell you. So, okay, and yeah, make sure that you have all the tools installed. Wait, what was I going to say? I don't remember. It's okay. Okay, questions? Yeah.
Is there anything extra we need to install, or is it just if the final project works, we have everything we need?
If the final project works, you have everything you need. Yeah. That's the other thing. Git SSH key. Yeah. So which I assume you probably should already have. Yeah. Question.
The link to request a partner is broken.
I saw that Piazza post. Let me make sure. Let me make a quick note to fix that. Yeah. Okay. The quiz for today?
Yeah.
Very soon. I need to finish one question. Okay. Any other questions? Yes?
Do you need SDL working for the final?
You do not need SDL. For the final exam, yes. SSH key, yeah. There will be a portion that requires you to use GitHub. So, but you will not be submitting through GitHub, but you will need to, at some point, pull and push something from GitHub. And in order to do that, you need to have your Git SSH key set up. Probably. Probably. I don't know. Yeah.
What resources are you like reserving? Is it open internet or just what you can?
That's a great question. Wait, let me remember what I actually have last year's rules right here. Yes, I say that you are allowed to use internet resources. However, you are not allowed to use any LLMs or AI or messaging apps. Yeah. Is the mic on? So, is there a question that anyone would like me to go over? Yeah? They are not. So a pure function, remember, is a function that cannot modify external state. Instead, when it receives input, like a bunch of arguments, it will always deterministically return the same output. You can think of like square root or floor or round or anything where you pass in some sort of value and you will always get back the same like thing. Like it doesn't matter what day of the week it is, it will always return the same output. That is what a pure function is. Yeah, and the idea with pure functions is that generally they're more readable because it's very clear what that function does. Okay, sure. Yes, question? Oh, sure. Yeah, so const eval. Okay, const eval. What does const eval require? Do you remember? If you have a const eval function, can it be run at compile time? Okay. Yes, it can. If you have a const eval function, can it be run at runtime? No. If a const eval function must always be run at compile time. That's different from a const expression function. Const expression means that it can be run at runtime as well. When you have a const expression variable, then that means that that variable only exists at compile time. So const expression variables must only exist at compile time. And const eval functions can only be run at compile time. Okay, so we'll go over a couple more of this. Clearly, this is a very long quiz. I lied to you. You actually have the full week to work on this. But let's go and talk through some of the questions. I might also give you a few other questions. This is actually part one of your study guide for the final exam. So, okay, are there any other questions? I can also spend more time on questions 2 or 3. Yeah, okay, questions? Yeah. Number 9. What part about it?
Yeah, so what happens to the negatives when it's converted to the unsigned type?
Mm-hmm.
Does it like get treated as, like, does the signed bit get treated as part of the number, or does it get truncated like 0?
So when you take let's say you take -1 and you pass that into an unsigned integer like parameter. So here we have an unsigned a, right? What would happen if we passed -1 into this? What would the resulting number be? If we passed -1 into this, what would happen? Would it be -1? Yeah, it'd be like 16,000 or 16 million or whatever. Yeah. So therefore, if we, like, for example, ran this function right here, what would happen is, like, you would expect it to be like, oh, like, is this first variable less than this variable? It's like you would expect it to be yes. But instead, since this one is an unsigned integer, in this case, this will be what number for this? Yeah, exactly. This will be like 16 million, and it'll check, is 16 million less than 2? And is this true? No. So this will return 0. So for example, for F4, at least you know that this will be 0. So in this case, the answer will not be all ones, okay? Yeah, and so you just go through. You just check, like, oh, so if I'm passing in a negative integer here, which it looks like it's all the first case. So if I pass in a negative integer to, like, this value, okay, in this case, what will the answer be? This will be true, yeah, because it's -1 is less than 2. Okay, what about here? Yeah, this will be, is 16 million less than 2? Okay, makes sense. Cool. Any other questions? Yeah.
Relatedly, for F3, when you're comparing an integer and an unsigned integer, do they pass the unsigned integer to a signed integer, or do they pass the signed integer to an unsigned integer?
So when you're doing this, what happens is it treats them both as the value that they actually store. Like in this case, this is storing in a signed integer, which is -1. It is comparing -1 against the unsigned value of 2. So it's just checking those actual values. Yeah. So in this case, what will the result be? This will be true, yeah, because in fact, -1 is less than unsigned 2. Sure, yeah, good question. Another question? Yeah. So this is just something that you'll have to memorize. I don't remember how much time I spent on this, but hopefully you at least experimented a little bit in your final projects. So this question, what Git command combines 2 branches and preserves the commit history of both branches? So in this case, this would be a merge, because you are merging both branches together, versus when you in this case, when you rewrite all commits from one branch and then place them linearly after the other branch, this would be a rebase. You can think of like rebase being like destructive, like it rewrites your history, versus merge, it just kind of merges them together, like puts them together. And what merge will do is it will create a new commit, and that new commit will probably say something like, oh, like merged main, or merged like this into main or something. So that is what a merge is it creates a new commit, but rebase does not add that new commit, but it destroys your history. Both are reasonable, but it's important to know the difference. Does that answer? Yeah. Okay. Yeah, question? I will, change it to be due on Friday, and I will give you more attempts on this. Yeah. What was it, 10? 10. Okay, this is the last question I'm going to go over. So number 10, observe the following workflow file. Okay, I actually don't remember all of this. So is there a point on this in particular that you're confused about? Oh, sure. So the workflow file will produce an error if main.cpp is not formatted to rules specified by Clang format style Google. Okay. So here we can see Clang format style Google. So will this workflow file produce an error if the file is not properly formatted? Actually, yeah, it won't produce an error. Why will it not produce an error? Exactly. It actually needs, it needs dry run W warning or whatever. Yeah, W error. Yeah, exactly. Question? Oh, yep. It is asking for a generic, correctly working format job. Yeah, good question. I probably should have clarified that. Yeah. All right. Any other final questions on anything? Last question. It's saying if you run this error or this workflow right now and it fails, like let's just assume it fails, maybe what happens is Clang format was not cached properly or something. Maybe apt was broken that day or something, and this workflow failed. Then the question is like, is this code that you push, is the commit still allowed to exist on the main branch? Yeah. And is that the case? Yes, it is. Okay. Cool. Okay. Well, that we're a little over, so I will extend this quiz. Yeah, this will act as at least part of your study guide. We'll release some more study materials. On Wednesday and Friday, we will continue kind of just talking about the random things. I think I'll make a Piazza post asking for more inputs on things to talk about. Cool. Okay. See you on Wednesday.